Hello everyone, welcome back. In today's video I would like to discuss the idea of a potential function. Last video we discovered that we can write a gradient field such that I can have the gradient of some function f, and I come from f and I go to f, and then this is some vector set of partial derivatives. So I could have partial x1 of f, partial x2 of f, then all the way down to partial x3, or partial xn of f, given some n-dimensional function. Anyways, what I'd like to do now is consider the idea of taking this vector field, so this is now a vector field of dimension n, and I would like to reverse the process. So given some f, so given some potential function f, can I go and find f such that the gradient of this function is equal to f, the vector field, right? So what's really interesting about this is its application to physics. Now, when we have a gradient, we need to remember what that was. So a gradient was really given some level curve of a function. So say this is a three-dimensional function, and I'm taking a level curve, and this is the xy plane. And so say it's a parabola, and say this is for some constant k equals c or something like that, and I have f of xy equal to this k, right? So what we're given is we're given a two-dimensional graph, and what we can do with that is remember that the gradient is a vector field, and what the gradient shows us is a normal vector to our level curve. So this is perpendicular, it's normal to our curve here. Now what's interesting is we can say that this here is the potential. This is the potential function, a level curve of the potential function. When we take the negative of the gradient, we get the force. So this is the force. So given this potential energy level, I'll have a force that points in this direction. So what we say is we can call the potential energy V. So if I have V, I can go to the force through the equation nabla V, or negative nabla V, is equal to the force field, right? Now you may have seen in calculus-based physics that the force is equal to the negative potential derivative with respect to whatever variable you're dealing with. Obviously that's a single variable idea, but we have other ideas. And what we saw in the single variable case is you could be given some potential function that looks like that. You can determine which points are stable and which are not. So for example, this point here would be a stable equilibrium, because if I have a particle here, it's going to stay there. If I move it up here, it's going to roll back down there, and if I roll it up here, it's going to move back down there. Now, also here, the derivative is 0. The force would be 0 then. But if I move it just a little bit, like over there, it's going to fall all the way down to this minimum. Anyways, what we're doing here is we're just generalizing this to multiple dimensions. But anyways, I'm digressing a bit. We want to look at the process of going from a force over to a potential. Obviously, for a single variable case, that's easy. It's an integral. But we need to examine a process for reversing the gradient, right? So given some force field, derive some potential function such that the gradient of that function is f. And there's a uniqueness theorem here that says that if I can find some function such that its gradient is equal to the force field, then this is it. This is the only function it can be, up to some additive constant. So I get some f plus c, right? And the c goes away because we take all the partial derivatives for this. But anyways, if I'm able to find this f, then that's the one it's going to be. That's the one it's got to be, right? So let's try an example. Let's try finding the potential function for this vector field such that f is equal to 2xy cubed z to the fourth, 3x squared y squared z to the fourth, and 4x squared y cubed z cubed. Now, first, obviously, you need to determine that that the vector field is conservative, which is easy enough to do, and that's the criteria for having a potential function. So there wouldn't be a potential function if this force was not conservative. But anyways, let's see if we can try to find this. So we know that because this is a gradient of the potential function, we can write all of these as partial derivatives. So the partial derivative with respect to x is 2xy cubed z to the fourth. The y derivative is 3x squared y squared z to the fourth. And the z derivative is 4x squared y cubed z cubed, right? So what we're going to do here is we are going to try to integrate each of these, and we're going to see what we get when we integrate each of these. But the process is a little bit, it's a little bit funky, I think. It really requires a lot of shoehorning to make sure that you get it. But if you're able to get something and you take its gradient against the function, then you're done, right? So let's try reversing the x partial derivative on this here. So we get that f is equal to the integral of 2x y cubed z to the fourth dx. Now when we integrate this, we take out y cubed z to the fourth as constant, so integrate 2x, we get x squared y cubed z to the fourth. But instead of having a constant of integration, we have a function of integration, because f can still depend on other variables of y and z, because the x derivative would kill those anyways. Because if I had the function be like x cubed sine of yz, x cubed plus sine of yz, and I took its partial derivative with respect to x, then this would go away entirely. So we need to account for that. So that's why we add this function of integration. Then we can try integrating with respect to y of this y component of the y partial derivative. So we get x squared y cubed z to the fourth. Oh, this is working out nice, isn't it? And then plus a function of x and z. Finally, if we take the z derivative and integrate that with respect to z, we get x squared y cubed z to the fourth again. Now, what we have here is all of these are the same. That means that these don't really matter anymore because these are all the same. And if we try to take this gradient, we'll return to our potential function, or to our gradient. Now, thus, we can say that f is equal to x squared y cubed z to the fourth plus some constant of integration. We need to remember the constant of integration. Even though we use these functions of integration, the gradient will still kill out any of these constants because the derivatives kill out any of the constants. So we need to keep them here. And thus we've determined a potential function such that its gradient is equal to the force. All right, so again, what this means is that I have some sort of potential, and if I negated this gradient, I would end up getting some sort of surface. Maybe like a paraboloid or something. Not for this, but just for the general example, because that's what I can draw the best. There's our paraboloid. And what we would get is we'd get vectors that point inwards on the surface, normal to the graph. And what that would really say is which way is our, if I were to put a ball inside of this bowl here, which way would it go? What force would it feel? Where would it want to go? Right? So that's really what that means. All right. So in the next video, we're going to start diving into some new material, talk about line integrals, and then we will be moving on to kind of bump that up to multiple dimensions. So really, we're just going to be taking what we did in single variable calculus and then in the multivariable integrations, just generalizing it to surfaces of general shapes instead of just kind of surfaces that we just wanted to integrate. So we'll talk about that. Thanks for watching. We'll see you in the next one.